they retain, of course, from the morphine, we have removed ring B, we have removed ring C, and now we are left with the phenyl ring and the piperidine ring, and no wonder phenyl piperidine. So, of course, when we look at fentanyl being, of course, an example of the 4-phenyl piperidines, but being more specific, an anhydride piperidine, which I'm going to discuss, we are saying this indeed is our phenyl group there, and that is our piperidine group. And I had asked you to draw out the structure so that you can be able to see how these groups are joined together. For instance, if you look at fentanyl, you remember I did mention that fentanyl is one of the drugs where you have a substituent at that position. Remember, this is supposed to be our quaternary carbon, but fentanyl does not have a quaternary carbon at this position. It has a hydrogen, and you can see from its structure that is very, very clear. And then, of course, we did mention that in these compounds which we are going to discuss, and they are called the anhydropiperidines, there is a nitrogen there, which is between the phenyl group and the piperidine group. And for sure, that also will bring a difference. Again, if you look at fentanyl, again, you can see this is a group that we have discussed a lot. That is the phenethyl group. That is a group we have said it is able to interact with the receptor site A, and therefore give these compounds a lot of activity. So I hope you have drawn some of the structures out, because in drawing them out, you're able to understand what kind of compounds that we are talking about. So if you look at loperamide, which also is a phenyl piperidine, you can see it has, of course, it is a little bit modified in that it has very, very huge groups. If you look at it, it has very, very huge groups. You can see that is a phenyl group there. Phenyl group there, again, attached to, this is supposed to be a quaternary carbon. But again, remember, we did mention that there are exceptions to that rule. And even for the loperamide, there is an exception. That is not a quaternary carbon. It has a hydroxyl group. And we do require that hydroxyl group because if you look at this structure, it is majorly hydrophilic. It is majorly hydrocarbon. And therefore, we do require at least to give it a bit of water solubility for it to go into solution, and then it's absorbed. So, and then if it requires to be absorbed, it is absorbed. But because, again, if you look at this compound, has very high lipid solubility, and therefore, indeed, it is not absorbed. It remains in the GIT and acts mainly in the GIT. A bit of it can be absorbed, but none of it will cross the BBB. This compound is not able to cross the BBB because of depolarization, high plasma binding, and therefore, it retains its activity in the GIT. But when you look at it, as I have said, you can see that is our phenyl group, as we have discussed, and this is our piperidine group there. But now, on the terminal nitrogen, you can see the huge group that is put there with very high lipid solubility. And the same case applies to this other example, which we call the diphenoxylate. Again, we look at the diphenoxylate. At least the diphenoxylate has the quaternary carbon there, and that's the phenyl group and phenyl piperidine. And just like the others, it has also another substituent. It has an ester substituent at that position. But of course, we need to understand whenever you have an ester substituent or whenever you have an ester substituent, that drug can easily be hydrolyzed. And of course, in the body, you can see also here, it has the nitrile group. And again, when you look at this compound, it is majorly hydrophobic. And again, as we had discussed, or as we are going to discuss, it's mainly retained in the GIT for to act as an antidiarrheal agent. We also mentioned, so fentanyl, of course, is used as an anesthetic. And of course, also you have lofentanyl, just to compare the structures. And when you look at lofentanyl, again, you see the slight differences. It has, on its piperidine, it has a beta methyl group on the piperidine ring. And we did mention when you have a beta methyl group there, again, there is an enantiometric conformation or change in that molecule to give it much, much, much higher activity. Of course, we did mention that when we were looking at the proteins. But this, of course, is not a protein, because if it's a protein, it also would have to have it's not a protein, because if you look at its structure, it's different. It has this nitrogen, so it is still an anhydride. It is still an anhydropiperidine. But from what we have discussed, addition of that methyl group there increases activity. Then when you look at it also, you will see that this is an ester there. That is an ester there. And that ester, as compared, if you look at that ester, what we did mention, in fentanyl, we do not have a substituent there. What we have is a hydrogen. So again, esters are highly labile. They are easily hydrolyzed in vivo to give, of course, inactive compounds. This was just to draw a few of the structures so that we can be able to see them visually and understand exactly what we're talking about. I believe we discussed meperidine as our prototype. You can actually tell me, I think we went all up to here. We discussed that. We discussed this, 4-phenylpiperidine, stereochemistry. And of course, we are saying that the highest activity even of meperidine is when it carries it has that axial orientation rather than the horizontal orientation. And with that axial orientation, it means that drug has the conformation that is necessary to interact with the receptor appropriately, to interact with the receptor appropriately and give us a maximum activity. And indeed, we did discuss all this. And of course, these are where we had the proteins. And where we had the proteins, we talked about that you could have a methyl group at position number 3 with the proteins. Methyl group at position number 3, position 1, 2, 3. And again, we did discuss that the orientation of this group is very important. This group can be alpha or it can be beta. If it is alpha, it means alpha or axial. When it is axial, you find that that compound, because of the fact that there is some steric hydrons with the benzene ring, then you find that that compound does not have as good binding as when it is beta. So when it is alpha, which we call the trans protein, we discussed that last time, transprotein, alpha or axial. We mentioned that that compound will be twice as active as morphine, but that group can also carry the beta orientation, or we can carry what we are carrying. We're saying it can be horizontal and therefore not carry the same orientation with the benzene ring. And in carrying the horizontal orientation, which we are calling the Cs, but we are calling it Cs because in respect to this group, not in respect to that particular group. We're calling it in respect to that group, that the methyl group and this other group, the propoxy group are actually the bigger groups are in the same, are actually facing the same, on the same side of the rigid bond, and that's why we are calling it Cs. And we did mention when you have these, when the methyl group is carrying the beta orientation, or it is having the beta orientation, then we have the beta protein, or the horizontal orientation. It has the beta protein much more active than the alpha, much more active than morphine. But the higher the activity, for sure, the higher the toxicity. So you find that there is preference of the alpha proteins because of the lower dependence, the lower toxicity as compared to the beta proteins. I think that all this we had discussed, and I think that was our last slide, where we were looking at the stereochemistry of the methyl group at position number 3 of the piperidine ring, of the phenylpiperidines. And they say that methyl group, its orientation is very important, because its orientation has an influence on the ability of the phenyl ring to interact. Remember, the phenyl ring to interact with the receptor appropriately. So that is the only influence that it has, that it influence the way the phenyl ring is able to interact with the receptor and therefore have an influence on the activity. So I think that was our last slide. And then we can continue. So, and as we look at that compound, the proteins, there's something I mentioned last time, that not only do we have insert that group there, we have a reversal of the ester. This is reversal of the ester. Because if you look at all the other 4-phenylpiperidines, you start with the C double bond O. And then you go to the oxygen. So that is how the ester is supposed to be. Start with the C double bond O, and then go to the oxygen. When you start with the oxygen, this is the reversal of the ester. This gives these compounds a little bit stability in that the reversed ester is not readily hydrolyzed by the esterases. So it gives these compounds a bit of stability. But the only unfortunate bit is that these compounds, the reverse esters, have an ability of forming compounds that are toxic, or what we call compounds that are neurotoxic. So although they have more stability, better activity, higher activity, there is a danger in that they can also be neurotoxic, or they can precipitate Parkinsonism, and that is a danger of these compounds. So we cannot, another molecular modification that stabilizes a molecule, that is this compound here, which we are calling our proteins, is reversal of the ester. So you can see this reversal of the ester, as we have talked, the meperidine reverse ester, which we can call N-methyl phenyl 4-propionoxy piperidine. So we are calling it N-methyl. So N-methyl phenyl there, and then 4, because this group is at position 4, and we are calling it propionoxy because we are, if you look at it, this is the propyl group there. Propyl group there, but because of the oxygen, that's why we are calling it propionoxy, because it has that propyl group, but then you have the oxygen, and therefore propionoxy group because of that oxygen. And as we have said, it is a reversed ester, and because of that reverse ester, it can give us this compound. So it can undergo. So that's what we are saying, as the meperidine reverse ester, that which we are calling MPPP, has a longer duration of action due to increased resistance to ester hydrolysis, as I just said. But unfortunately, the reversal of the ester group converts a stable group into a living group in vitro. So it converts this stable group here into a living group. So it easily leaves. It is more stable to esters, but the whole group can readily leave. And if that happens, then in vitro, that produces MPTP upon decomposition, which is converted to MPP by monoamine oxidases. And the MPTP is 1-methyl-4-phenyl 1,2,3,6 tetrahydropyridine. If you look at this, this is the pyridine, is this compound. That is a pyridine. So it has aromaticity throughout. So when you look at these as a derivative of pyridine, you have removed 2 bonds, and in removing 2 bonds, you have added 4 hydrogens, and that's why we are calling it tetrahydropyridine. The 1, 2, 3, 6 is just to show the positions within that molecule where you have done, you have saturated. So of course, pyridine is aromatic with a lot of unsaturation, but now when you convert, or when the reverse ester undergoes cleavage in vitro, then you find that it forms this compound. And then this compound is what we are saying. If you have that compound formed in the body, if you have the MPTP, which can still form in vivo, if you have it formed in vivo, then it will be converted again to this other compound here. And if you look at this compound here, that compound, all that has happened is that this methyl group there, that nitrogen, the nitrogen of that methyl group has gained a hydrogen. That's the only difference. So it's just protonation of that nitrogen, because that nitrogen is basic in nature. So it undergoes protonation, and now this group converts now from the tetrahydropyridine to the pyridinium. So this now is pyridinium. That's the only difference. And that can happen in the body. And if that happens in the body where it is catalyzed by monoamine oxidase, this is a compound we are talking about as having a lot of toxicity. So that is what we are saying. Introduction of a methyl to MPPP at position number 3 results in stereoisomers having different potencies. That we have already said the trans-methyl is called alpha protein, and the cis isomer is the beta protein. Their respective potencies are 5 and 14 times of meperidine. So we are saying introduction of that, which we had already mentioned, then that results in stereochemical change or conformational change in the resultant molecule and the binding of the molecule. But also, of course, that is accompanied, as I have already said, by reversal of the ester. So this is just to highlight what we have just said, that the 1-methyl-4-phenylpyridinium, that's a 1-methyl-4-phenylpyridinium. This is a compound that was found to have a lot of toxicity. It's a positively charged organic molecule. It is a neurotoxin that acts by interfering with the oxidative phosphorylation in mitochondria, leading to the depletion of ATP and eventually cell death. The MPP, which is this MPP plus 1-methyl-4-phenylpyridinium, pyridinium has a positive, rises in the body as a toxic metabolite of the closely related compound MPTP, which we have just discussed. It is converted in the brain to MPP plus by the enzyme monoamine oxidase B, ultimately causing Parkinsonism by killing certain dopamine-producing neurons in the substantia nigra. So all we are saying is that, unfortunately, the drug can be good, but you must be careful of the toxicity. So that is a side effect of the proteins, whereby, yes, they are more stable to ester hydrolysis because of the reversed ester, but the whole group can leave. The whole group can be cleaved as it's a good living group, and once it cleaves, if that happens in the body, then that compound ends up being toxic. So then the nitrogen substituent, you're still looking at the phenylpiperidines. The nitrogen substituent is methyl in most cases, but of course we have looked at so we are saying optimally it can be methyl. But when we look at the compounds under the phenylpiperidines, we have seen you can have different groups of that compound with retention of activity. If you have a phenethyl, as we have already said, even in all other compounds, there is, or its equivalent, there will be an increase in activity. Remember, we said when you enlarge that group, then it has good ability to interact with the site A of the opioid receptor. It is not possible to confer antagonist activity with a nitrogen substituent such as allyl as in morphine. In other words, remember we have said all along from morphine, morphinans, benzomorphans, that once you introduce an allyl, once you introduce a cyclomethyl group, whether cyclopropyl or cyclobutyl, then you bring in antagonistic activity. But we are saying for the 4-phenylpiperidines, you cannot. That introduction of those groups was not found to bring any antagonistic activity, and therefore we do not have those drugs. And if you look at the structures that we have, we do not have those drugs as part of the 4-phenylpiperidines. The SAR for the N substituent are very similar to that of the morphine derivatives, and introduction of an aryl substituent markedly increases activity. The this aryl is like you find in fentanyl. So that's the same point we had just said. If I increase it again, it's getting lost. If you look at the structure of fentanyl, this is the aryl phenethyl aryl as in fentanyl. So if you do introduce, it's just what we have said, a phenaryl group, there is there is drastic increase in activity. If you change this ring, that is the piperidine ring, you expand it or you make it smaller, then you find that you will interfere with the activity. And the reasons why you interfere with activity when you change the phenylpiperidines, when you change that ring to 5 or 7, is because, remember, the distance between the phenyl ring and the terminal nitrogen is very crucial. That distance is very crucial for maximum activity. So when you shrink it, when you do contraction or increase it, then you interfere with the distance between the phenyl ring and the terminal nitrogen. When you interfere with that distance, as we have said severally, you interfere with the ability of that molecule to interact with the opioid receptor, and therefore you will decrease activity. So expansion or contraction of the ring to 7 or 5 members gives compounds analgesic activity, but less mu receptor affinity due to a change in the relationship between nitrogen and the phenyl ring. So that can be done. That can be done. You can change that ring, as we have seen in quite a number of those drugs. You can contract those rings, but that will result in a decrease in activity. Then we have mentioned the diphenoxylate and the loperamide, and these are not narcotic analgesics. These are not opioid analgesics. These are antidiarrheal agents. The reason why they're used as antidiarrheal agents is that they do not cross the CNS to get to the opioid receptors. They are retained within the periphery because of their high lipid water partition coefficient, because of also their plasma binding. They do not cross the BBB, and therefore are very useful outside or peripherally. And indeed, they do not have much abuse potential because they do not bring about the effects of the narcotic or the opioids. So the diphenoxylate is highly lipophilic. However, in regular doses, it has no CNS activity due, one, to high protein binding and sequestering in the lipid bilayer. So it has very high lipid solubility, lipid water partition coefficient, and therefore it will have high protein binding. It will also undergo deportization, or what you call, say, it's sequestered within the bilayer, lipid bilayer, and therefore it will not be able to get into the CNS to bring us the effects of the opioid analgesics. It's also rapidly hydrolyzed to the carboxylic acid. So also this drug is also rapidly hydrolyzed to the carboxylic group. Because of this group there, you can get a carboxylic group there, and once this is a nitrile group, it can form a carboxylic group there. And once it does that, it gives you the diphenoxine. I think there's an E there, diphenoxine, which cannot again penetrate the blood-brain barrier. So again, those are the 3 reasons why diphenoxylate is mainly a peripheral drug. It's used in the periphery. It is used as an antidiarrheal agent, mainly not absorbed, because it is there is deportization within the lipid layers, and it has quite a lot of its activity within the GIT. We also have loperamide again, yes, but we had said, look at these structures. Although their activity is very different from that of the other opioid analgesics, there is a commonality. They share a similar structure, because you can see that is a phenyl group there. This is a group that is no others. And then, of course, you have this as our tertiary amine, quaternary carbon, and then you have the piperidine group, and the nitrogen has substitution. But it's only that group that is substituted on the nitrogen is so huge that it gives that compound different properties as compared to the other 4 phenyl piperidines. So it has also high lipid water partition coefficient, and it's also free of all CNS effects due to high protein binding, and it is twice as potent as diphenoxylate. Again, when you look at this compound, this is a loperamide. One of the other factors you see is the halogen, and we know halogens slow the metabolism. Halogens increase lipid solubility. These are things that you know by now. So this halogen will protect the phenyl ring from undergoing oxidative hydroxylation. It will increase again further the lipid solubility, again causing more retention of this drug within the periphery, and therefore no CNS activity. So it has twice as potent as diphenoxylate. Further, the high lipid solubility results in slow dissolution, resulting in very slow absorption, and only about 40% bioavailability. The lack of water solubility prevents the drug abuse because it cannot be injected. So this drug also, although it has having some absorption, you cannot, because of the very low water solubility, you cannot give it as an injectable. And therefore, when you come to these people They want to abuse these drugs mainly as injectable drugs. You cannot abuse it. In any cases, we have said, because of course, if it has a problem of deputization not being absorbed well, it would mean if you inject it, then of course it will hit to get high levels. But even when you inject it, it's still undergo deputization in the BBB because there is also a lipid layer. But we are saying that the fact that it has no water solubility is another advantage. You cannot formulate it into parenteral formulations, and therefore also lesser degree of abuse. So we are appreciating that structure modification of a compound. We are starting from morphine, and you can see how the structure has really been modified such that you get drugs that are really not narcotic analgesics, but they are anti-diarrheal agents, because one of the things that the narcotic analgesics cause is constipation. So you can use them to counteract diarrhea in patients who have diarrhea. And of course, we are saying the advantage is that they will not have a lot of those side effects. They could have a bit, but they will not have major narcotic analgesic side effects because of the fact that they are not well absorbed. They do not cross the BBB. Also, we have another drug we call the alfimopan. And when you look at this drug, this I think we have just discussed, and we have said that you cannot change the substituent at the nitrogen to you put an allyl group, you put a cyclomethyl group, so that you can have an antagonist. So this was one of the antagonists which was developed, one of the first antagonists of the 4-phenyl piperidines, but you can see that it does not have the group we have mentioned. It does not have an allyl group. It does not have a methyl cyclo group there. It has a completely different group, and that further emphasizes on the fact that the SAR of the nitrogen is that for the 4-phenyl piperidines is different, because we cannot make analgesics antagonists by changing that group as like in the other compounds that we have discussed. You can see this is one, and you can, as you look at it, you can see again it has a phenyl group there, which of course also has a hydroxyl group, but that it has a hydroxyl group there, and that hydroxyl group is a group that we have come across, in that the morphine has a hydroxyl group. Most of the other compounds have a hydroxyl group, which helps in hydrogen bonding at hydrophilic bonding at the receptor. And if you look at it again, this is our carbon there. So it has that group there, 1, 2, 3, 4. So it also has a quaternary carbon, which again agrees with the stereochemistry. It has also this beta methyl group, which is found in the proteins, but of course it's not a protein. So it has also that beta methyl group, which we have said that beta methyl group can increase activity. And then now it has this blood group here, and this blood group introduces antagonistic activity. So that was one of the first antagonists of the 4-phenyl piperidines. So we can say albumopan is a drug which behaves as a peripheral acting mu opioid receptor antagonist with a limited ability to cross the BBB and reach the mu opioid receptors of the central nervous system. Again, if you look at that drug, you look at it, you can see what's happening. That's a carboxylic group, that's an amino group, that's another. So it is highly hydrophilic, and therefore it is not able to penetrate the BBB. It has the limited ability to cross the BBB barrier and reach the mu opioid receptors of the central nervous system. The clinically undesirable effects of central acting opioids antagonists, like the reversal of opioid mediated analgesia, are avoided without affecting the intended blockade of mu opioid receptors in the GIT. In other words, this is a drug that can be used. It will not have those reversal effects. It will not cause withdrawal symptoms. It will not cause withdrawal symptoms, but it can, and also it is not. It of course is not crossing the BBB, but we are saying it can be used for blockade of mu opioid receptors in the GIT. This one is blocking. It's not an agonist. So that's the difference between this one and the loperamide and the diphenoxylate, the diphenoxylate, then the loperamide. Those ones are agonists. This one is an antagonist at the GIT. It works by protecting the bowel from the also constipation effect of opioid narcotic medications that are used to treat pain after surgery. It's also approved for the treatment of post-operative ileus, disruption of the normal propulsive ability of the intestine. So it also does have some activity within the GIT. It is one of the first antagonists, and it has been found. And being an antagonist, that means you can understand why it can act. You can understand why it can act as an antidiarrheal agent, because it will block. It will block. It will block the activity of these drugs, or the morphine. These drugs like morphine. If you have it will block the binding of constipation, of the opioid of narcotics. So if you have taken narcotics and you take it together, it will block the receptors within the GIT where the opioids bind to bring constipation, and therefore it can be used to protect the effect of constipation brought about by narcotic analgesics. As we are saying, it can also be used for postoperative ileus, which is a normal propulsive ability of a disruption of the normal propulsive ability of the intestines. In other words, it's like the intestines have relaxed and they are not undergoing the peristalsis. Remember that peristalsis movement. So when you give this drug, it can prevent that. That especially occurs if you have an operation in the GIT for the intestines to go back, to get back their tone and everything else. Can take time. So we're saying you can give this drug to help you in regaining the peristaltic movement of the GIT after an operation. So I was giving that at least to give us an example of one of the antagonists. And when we compare it with all the other antagonists we have looked at, we have, of course, observed that the structure is completely different. Niko class, acha nikuongea nikimaliza. Niko class. So now, from that, we are still on the 4-phenyl piperidines, but under the 4-phenyl piperidines, we have the special class, which we have called the anilidopiperidines, and this is where the fentanyls, the remifentanil, and the others fall. And the only difference between this and the other groups within the 4-phenyl piperidines, as I had already said, is that between the phenyl and the quaternary carbon, there is a nitrogen. That's the only difference. And that nitrogen is said to be very important because, again, that nitrogen allows the phenyl ring to be able to be well oriented, to have the proper orientation to be able to interact with the receptor effectively. We will be able to see that the anilidopiperidines have a slight difference in the way they interact with the receptor, but that nitrogen and the nitrogen carbon oxygen bond are very important because they allow this group to attain the configuration or the configuration or the conformation rather, to attain the conformation or the shape that is able to interact with the receptor maximally. And because of that interaction of the receptor maximally of these drugs as compared to the other 4-phenyl piperidines, you find they have very rapid onset of activity, they are highly reactive, and no wonder they are even used as anesthetic drugs. They are used in theater. They are even used in theater to give analgesic active. They are used in theater for the purposes of analgesic activity. So moving the phenyl ring from the direct attachment to the piperidine ring by one atom to nitrogen on the side chain allows for the phenyl ring to assume the more favorable axial. Remember, we had said that the phenyl ring should be axial in relationship to the other compounds conformation. So or when you look at that, that is a piperidine, of course, and then you have the aniline. So you can see this is the aniline up to there. So you take that aniline there and you join it to position to our quaternary carbon. So the others, this phenyl ring is attached directly. So you put a nitrogen in between, and all we are saying, the minute that nitrogen is introduced in that position, this molecule is able to attain the conformation that is best in the conformation that has been found to be most favorable in interacting with the receptor. Thus, here is my granddaughter. Okay. All right. Just give me 1 minute. We are saying that nitrogen is very important in attaining the right conformation. That's the phenyl ring of the anhydropiperidine binds the D site similar to the morphine A ring. Remember, we are only saying the binding is the same. So we are saying that that's the phenyl ring of the anhydropiperidine binds the D. You see, the D is what you start with, and that is the same position that is bound by ring A, the phenyl ring of morphine. And the 3-hydroxyl group is not essential for binding this site, and therefore you find the phenylpiperidines do not have. Of course, that is for the phenylpiperidines, because remember we said for morphine, that hydroxyl group is necessary. But for the phenylpiperidines, we have to be very specific. You do not require the hydroxyl group to bind that site. For the morphine and morphine analogs, the hydroxyl group, of course, does not bind the D site. It binds another area where it is binding through hydrogen bonds. But for the phenylpiperidines, we do not require it. So we are therefore saying 3-hydroxyl group is not essential for binding to this site. This class includes some of the most potent synthetic analgesics. And no wonder we are saying we use them in theater. Fentanyl, which is 50 to 100, is 50 to 100 times more potent than morphine. It has mu receptor affinity due to binding. It is able to bind to A, B, C, and D sites. When you look at fentanyl, please do be reminded of this group there. And that big group there is able to bind the A site. So that group is able to bind the A site. On proper arrangement of this molecule, this is able to bind the D site. And therefore, it is, of course, the other hydrophobic parts. Of course, it still retains the hydrophobic area, which is in the piperidine ring, able to interact with the B. And then it still has the anionic site, so able to interact with all the parts of the receptor, including the A site, which morphine does not interact with. It also has high lipid water partition coefficient, and thus can be absorbed through the skin or oral mucosa. So again, it has this group there, which increases its lipid solubility. It has that group there. It has this portion. Of course, it has this carbonyl group, but you can see it doesn't have a lot of, it doesn't have excessive lipid solubility for deputization, but it has good enough lipid solubility, which allows it to have very rapid absorption and very rapid penetration, but it's not as high as when you look at the diphenoxylates and loperamides. And you can tell that from the structure. If you compare this with the diphenoxylate and loperamides, at this position, nitrogen, they have a diphenyl group. There are 2 phenyl groups, very high lipid solubility, and therefore it has just enough lipid solubility to allow it to be absorbed. It can be absorbed in the skin, through the oral, and also through the oral mucosa. And also we are saying it can penetrate the BBB to give us a rapid onset. But of course, also remember, drugs that have a rapid onset are also undergo deputization within the brain, and will also have a short duration of activity. And the nitrogen, as I had said, that is the nitrogen at carbon 4. Remember, this is our carbon 4. We have that nitrogen and the alkyl through the nitrogen carbon oxygen. So you can see that one there. We have this nitrogen, the nitrogen itself, and also this alkyl group through the nitrogen carbon carbonyl, this is a carbon oxygen bond, increase mu receptor affinity by correctly orienting the phenyl ring. So we are saying the nitrogen itself, together with the nitrogen, carbon, oxygen, correctly, and of course through the alkyl group, this is the alkyl group, orient the phenyl ring in the proper position such that we get, as we had said earlier, the correct conformation for this compound to really bind, for the phenyl ring to completely or maximally interact with the D receptor. So therefore, we are saying we can't be able to explain the increased activity of fentanyl. We can't be able to account for the higher analgesic activity of fentanyl or the piperidines by just looking at their structure. Then, of course, there is, of course, other compounds. If you look at remifentanil, the only difference, of course, with remifentanil is that if you look at it, of course, it has at position number here, where in fentanyl we have a hydrogen, it has an ester. It has an ester group there. That ester can be readily hydrolyzed. Again, at the nitrogen, it also has an ester, and that can give this compound slightly shorter duration of activity. So the esters on the nitrogen and on carbon 4 can lead to rapid inactivation of the fentanyl as compared to fentanyl. So lamifentanil can have a shorter duration of action than fentanyl, but you can see, as we have said, it also agrees. It has lower lipid solubility also. There you have an ester. There again, we have an ester. Those are groups that are not there within. Those are groups that are not there within the fentanyl, and therefore it has higher hydrophilicity compared to fentanyl. It has also labile or susceptible groups, the ester groups, and therefore a shorter duration of action. So those are two examples of the anilidopiperidines. And I think with that, we are able to understand why these groups or why these compounds have higher activity when we compare them with the other compounds. Then we go now to the last group. And in the last group, it is what we are now calling the phenyl propylamines. You can see propylamines, meaning that is a straight chain, or the diphenyl heptanones, phenyl propylamine. And in this one, all it means is that now the whole piperidine ring, we have cleaved it. So it is now open. So these are now open. They have an open, they do not have any ring apart from the phenyl ring. Remember from the beginning, we did mention that phenyl ring is very important for activity. And even as we move to the last group of the morphine analogs, we still see that the phenyl ring is retained, but the piperidine ring can be cleaved. But even as it's cleaved, there are still some properties or some features that will be maintained. That compound will have the tertiary nitrogen. The tertiary nitrogen will be separated from the phenyl ring with two carbon atoms, just like in morphine. It should have also a quaternary carbon atom. So although we have now cleaved and we have an open chain, we still have some of the morphine rules being obeyed for activity. Of course, we do have exceptions. We do not have the hydroxyl group on the phenyl ring, as in morphine and the other, the morphine, the benzomorphins, and so on. But we do have quite a number of the morphine rules are obeyed. And we have, so if you look at this compound again, this is a general structure, very, very simple. We are calling them heptanones because most of them do have at R3, one of the substituent is a ketone there. So that's why we call them diphenyl. And as we will see in most of them, one, let's say like R2 is usually also a phenyl group, and one of the other substituents is also a ketone, and that's why we are calling them diphenyl heptanones or the phenyl propylamines. And we are calling them again phenyl propylamines because we see that's a phenyl, and in one of these will be like a CH2, and CH3. So phenyl propylamines 1, 2, 3. Phenyl propylamines, we'll be able to see as we look at the structures. So we're looking at the examples of these drugs, we have, of course, again, the prototype, which is methadone. I believe you have heard of the drug methadone. And when you go to, for those who will have the opportunity to visit Madare, you will see quite a number of patients who are on detoxification are given methadone, because methadone does not have similar effects, doesn't have the CNS effects that are found in the narcotic analgesics, and yet it avoids you having the withdrawal effect. So they are given methadone so that they can take care of the withdrawal effect. So now we have, if you look at that compound, it has a cis, R2, as we have said, is a phenyl ring. R3 is a ketone. That's a ketone, C double bond O, C2H5. And then you can see when we look at methadone, because this group is almost the same in most of in the three starting compounds: methadone, isomethadone, normethadone. The only sometimes difference is the positioning of the methyl group. So when you look at methadone, you see methadone, this group is CH2, CH, CH3, and CH3. So this methyl group is very near, it is closest to the nitrogen. So this means it is branched very close to the nitrogen, and that is methadone. When we look at isomethadone, the only difference is that the methyl group is closer to the carbon that is attached to the phenyl ring. So that is the difference, and we will find that isomethadone will have slightly less activity than methadone. Now, when we look at normethadone is now where there is no branching at all. So you look at it, it will have CH2, CH2, and CH3. So normethadone, just from the word no branching. So it will have the least activity. Isomethadone, there is branching, but closer to the phenyl ring, whereas methadone, there is branching, but closer to the nitrogen. So if you were to say, consider that as an atom one, we can say in methadone, the alpha carbon is the one that is branched. In isomethadone, again, it is the beta carbon. Remember, we use this alpha and beta for both orientation and even for to show the position. So for isomethadone, it is a beta carbon that has branching. For normethadone, there is no branching at all. And indeed, that change in the branching, in the position of the methyl group. So indeed, methadone and isomethadone are positional isomers. They are positional isomers, and in that change of the position of the methyl group also has an influence of activity, again because of the way it introduces steric hydrons and the ability of that molecule to interact with the receptor. As we have already said, again, if you look at that compound, again, just it's a tertiary amine. So that principle or that concept is still retained. Remember, morphine is a tertiary amine. So we still have a tertiary amine with the dimethyl amino group, again, being responsible for maximum activity. But you can have, again, you can have change of that group. Like you can see this is the branching here next to the nitrogen, and then this continues now to the phenyl ring, and you can see now the terminal nitrogen here in dipanone is part of a piperidine ring with retention of activity. So again, the nitrogen can be incorporated into rings with retention of activity. The compound would have slightly lower activity, but nevertheless, the compound still does have activity. Again, we appreciate that the nitrogen is still tertiary. Nitrogen is still tertiary, and again, the branching here closest to the nitrogen as it is at that position. And again, that, of course, is more of a derivative of methadone and not isomethadone. Then you can also have alpha acetyl methadone, be alpha acetyl methadone, and alpha acetyl methadone, we mention it later. Alpha acetyl methadone is this drug here, alpha acetyl methadone. So you have this is a methadone where it has CH2, CH, CH3, and CH3, CH3. And you can see the carbon which has branching is the one next to the nitrogen. So that's this group here is what qualifies it to be methadone. Of course, methadone has the 2-phenyl ring, and all that has happened to methadone is that you derivatize it fast into the alcohol and you acetylate, and that's why we are calling it acetyl methadone. So you acetylate the hydroxyl derivative of methadone, and therefore the substituent that we are talking about here. So this substituent, so at this position, the substituent we are looking at here is the whole of this substituent, the whole of that substituent. So when you look at that substituent here, you have it, you look at it as per the substituent we have there. You are starting with the CH3 there, CH2, which is CH3 there, so that you understand, CH2, and then a CH. So this is where they have not shown. This is where the rest of the molecule, or where this is the position of this substituent where it is joined onto the quaternary carbon. So you have the whole substituent is, as I've said, that is a CH3, that is a CH2, standing represented by CH3, CH2, and then you have this CH there, which is that CH, and then you move on. So we are moving on along this substituent like that. So you move on, and then you go to the oxygen, which is at oxygen, and then you go to the C double bond O, and CH3. So that is what we are calling the alpha acetyl methadone. But for that, or we are going to come across it later. But for us to get that compound, we are actually acetylating. You are acetylating the alcohol of methadone. So you acetylate the alcohol of methadone. If you acetylate the alcohol of methadone, you get alpha acetyl methadone. Again, if you look at this, the group is as found in methadone. Then there is the dextromoramide. I think that one I also drew it so that we can be able to appreciate. And the joining is at this position. They haven't shown. It is at that position. So you can see again, it agrees with all what we have discussed, the 2-phenyl groups, and then you look at that way, you go that way, you go this way, and therefore you can see this branching is nearer the phenyl ring. So this is a derivative of isomethadone, and then you have the nitrogen, so the 2 carbon atoms, the nitrogen, and this is the morphorin ring. I believe we have come across that ring with you before. So you have the morphorin ring. Again, the nitrogen is part, just like we had discussed earlier in the other drug, which we called dipanone. The nitrogen is also part of a morphorin ring or a heterocyclic ring, again with retention of activity. Why I want us to look at those structures is, again, because it's important that when we mention those, when we come to the SAR and mention some of those things, then you are able to understand, to be able to give examples from what we have already discussed. So that is very similar. Again, this is also the same nitrogen part of the morphorin ring. It is only that now, of course, here there is branching, and then this is a CH2, which is joined directly now to the quaternary carbon. So very, very close to the previous drug. Then we have the compound we call propoxyphene or dextropropoxyphene. This one, you look at it on its own because it has quite some difference. If you look, we are going to discuss propoxyphene, and if you look at propoxyphene, one of the differences you can note, I hope, okay, patie kitabu hata enda kuandika tena pale tamwangalia pia So if you look at propoxyphene, then you note, I hope you can note, one of the major differences is that whereas all the other compounds have a benzene ring, propoxyphene has a benzyl ring. That, of course, contributes to its reduction in activity. So it has a benzyl ring there, and that makes a difference. If you look at this group again here, it is very similar to methadone, very, very similar to methadone, and that again gives it a bit of activity. This group here, when we look at it, I believe it's supposed to be a reverse ester, but we're going to look at the structure. But propoxyphene, because of the difference in its structure, has very low analgesic activity, and indeed dextropropoxyphene, as already we have mentioned, the dextro along the way is mainly used as an antitussive, and it is found in quite a number of the cough syrups for its antitussive activity. But again, we mentioned that compound again. So we are now looking at the phenyl propylamines, and we have said, the diphenyl heptanones, and we have said that these are drugs that whereby the piperidine ring is open completely. Piperidine ring is open, and by opening that ring, somehow we reduce the analgesic activity, even as compared to morphine. But do remember, for the structure of morphine, if you open up that ring, you completely destroy activity. So we must understand that the opening of the ring is only when now we are talking about the phenylpropylamine structure. But you cannot open the ring of morphine. You can't open the ring of the benzomorphins. You cannot open the ring of the morphinans. You can't even open the ring of the phenylpiperidines. If you do so, you will lose activity. But now when you structurally modify these compounds and you come up with the phenylpropylamine, it is such that that compound still attains analgesic activity, although lower compared to morphine and the other drugs. So the prototype is methadone, as we have already said. It can be viewed as a ring D opened phenylpiperidine. And if you open ring D in morphine, there is a total loss of activity. So you've opened the ring D in morphine, you have a total loss of activity. Okay, you will give me 1 minute. Today, she's gone. Auntie, Auntie. Bye, bye, bye. Sorry for that small interruption. So we are therefore have said clearly that if we open the ring D of morphine, there will be total loss of activity. But racemic methadone is equal to morphine in analgesic potency. So we are only saying that morphine itself must be that structure. If you change it, then you will lose activity totally. But if you structurally modify to get another molecule, which is a phenyl propylamine molecule, then you retain activity. Both phenyl rings are required for potency. So both phenyl rings are required for potency. Removal of one sharply reduces potency. It may so if you remove any of those rings, then again you reduce activity. It may help correct positioning of one phenyl with correct spacing to the protonated amine for the anionic site. Again, the same thing we've been saying, that the second ring, so you have the first ring, but the second ring seems again to give us the proper positioning of the second phenyl and the terminal nitrogen. You know, the terminal nitrogen has an ionic site. So it gives you the proper distance between the phenyl ring for interaction with the D site and also the terminal nitrogen, which is an ionic for its interaction through an ionic bond. Again, therefore, a phenyl ring is necessary for maximum. For this time, it is maximum because we have said one sharply reduces, but the activity is not lost. So you require the two phenyl rings. If you remove one, there will be a reduction in activity. The phenyl ring of the phenylpropylamines binds to the D, again, as we have been discussing, site analogous to the A ring of morphine. So the phenyl ring of the phenylpropylamines binds to the D site analogous to the A ring of morphine rather than the A site, as we saw with the phenylpiperidines. So we are only saying that the phenyl ring, this phenyl ring, the phenyl ring of the phenyl binds again to the D site, analogous to the A ring of morphine. I don't know whether, I hope we mentioned this, that anyway, we'll go back to it to confirm that's what we said. So we are only saying that the phenyl ring, again, just like in morphine, the phenyl ring of the propylamines will bind again to the D side. Remember, we start with the D, and then we go to the C, and then we go to the B, and then we go to the A. So we are saying the phenyl ring of the phenyl propylamine again binds to the DC site, analogous with the A ring of morphine. We will go back here to confirm that is what we said, as we saw with the phenylpiperidines. They have high lipid water partition coefficient or high lipid solubility, low fast pass effect due to they are metabolically stable. It is not an ester, but a ketone, also has a long life. All we are saying, if you look at the phenyl piperidines, sorry, phenyl propylamines, we also call them heptanones. Heptanone means it's a ketone. And ketones, as you can see, are more stable. The ketones are more stable than esters, and that is why we are saying they are metabolically stable compared to some of those other drugs. But as of course, we have already said, although they are metabolically stable and therefore can have a slightly longer duration of action, they already have reduced activity compared even to the phenylpiperidines. They are stable because most of the others are esters, but nevertheless, they do have already lower potency. So they can have stability, they can have longer duration of activity, but we are starting from a compound that has lower activity. They also have they have high lipid water partition coefficient. You can see they have the two phenyl rings. Also, they have these alkyl groups. The position of these compounds, their polar groups are minimal, so they will also have high lipid water partition coefficient, and they have low fast pass metabolism because they are not esters. Esters are the ones which have a very high fast pass metabolism, and they are of course also stable, as we have said, because they are ketones and not esters, and therefore they will have a long duration of action. End substitution, and we have looked at some of the end substitution because when we were looking at the various compounds, we have looked at the end substitution, and we are saying when we look at like methadone, isomethadone, isomethadone, we say that the best is of course the dimethylamino group. But when you look at other compounds like the dextromoramide, looked at the other compound that we call the dipanone, we said yes, the nitrogen must be tertiary. It can be part of a cyclic ring, of a heterocyclic ring with retention of activity. So these are some things we have mentioned, but let us now look at what we are saying in black and white. Generally, the dimethylamino group gives optimal potency. As we have said, the diethyl derivative is less potent. The ethyl is less potent, but you can see when we put a cyclic group or heterocyclic group, as we have always said, although you could be having an ethyl group, that introduces a strain. And sometimes when you put a heterocyclic ring, or it could be a piperidine ring, because of the fact that it is cyclic, the cyclic nature of that ring introduces a strain and still allows for the proper interaction of the nitrogen, or proper distance between the nitrogen and the phenyl ring for maximum activity. So diethyl amino derivative is less potent, but if you have 5 and 6 membered alicyclic basic units, they have comparable activity, the dimethyl amino group. And that is why we have talked about the compounds that have the morpholine ring, the compounds that have the piperidine ring, because of the fact that there is strain in cyclic rings. There is strain, and therefore you're still able to attain the distance that you require for activity. The 2-carbon chain between the basic nitrogen and the quaternary carbon is its optimal length. Again, I showed you that. If you look at the nitrogen in methadone and you look at the quaternary carbon, you have 2 atoms separating. And in all those compounds, again, that rule, that part of the morphine rule is maintained. It is separation with 2 carbon atoms. Removal of the 6-alpha methyl methadone decreases activity. Remember, if you look at methadone, you do have an alpha. You do have an alpha group for methadone. If you look at methadone, you have a beta methyl group. They are also only saying when you start with methadone, which has an alpha methyl group, the removal of that alpha methyl group, you will decrease potency. Moving to the 6-alpha methyl to position number 5, gives also isomethadone, which is the beta position. They are in reference to nitrogen. Nitrogen would be the alpha, and the next carbon would be the beta position. Gives isomethadone, which has 65% of the potency. So again, also changing the methyl group from alpha to beta also decreases activity. The ketone side chain, which we've already looked at, is important for activity. And indeed, all those compounds do have the ketone, with the exception, I think, of the propoxyphene, and therefore less activity. The ketone side chain is important for activity. Removal or altering its length abolishes or significantly decreases activity. So if you look at that group, it's a C double bond O C2H5. That is a propoxyl group. It is the is it the propoxyl? Propyl. We do propyl. Propyl. I think it's a propyl group. So that group, I'll get the correct name. So that group, which if you look at it, is a C double bond O. It is an acyl group. It is an acyl group because of the carbonyl group, C double bond O, C2H5. That's why we are calling it. Actually, it can be called propoxyl group because that's the oxygen. So C double bond O, CH2, CH3, that group, as I've said, I'll get the completely correct name because we cannot guess. That group is necessary for activity. You cannot increase it to 4 carbon atoms. You cannot remove it. If you do so, then you will significantly alter or abolish the activity. Ketone is necessary. It is stable than the alcohol and therefore is responsible for good activity. Reduction of the ketone produces methadone. So if you reduce that ketone, you get methadone with decreased potency. So we have said we do require that group to remain as a ketone for maximum activity. All the above modification result in changing the distance and orientation of the basic amine and the phenyl group. As we have said, we require that distance between the terminal nitrogen and the phenyl group. That distance needs to remain to remain as the optimal distance to allow us to have maximum interaction with the receptor. So this is where, so now we are still moving on with the SAR. Then we are saying acetylating the alcohol produces a more potent analgesic. Acetylating the alcohol produces a more potent analgesic. The laboratory isomer is marketed as levomethadyl acetate. A single dose can suppress withdrawal for 3 days and is used in the rehabilitation programs. The levo isomer is 5 times more potent than the dextroisomer. Or we had mentioned this compound, the one we called the acetyl, alpha acetyl methadone. Remember the alpha acetyl methadone. If you look at it, this is the same compound, levomethadyl. And all we have said, remember we have said, if you have the alcohol, if you have the alcohol, if you have the alcohol of methadone, and the alcohol of methadone is where you have CH3, CH2, and this group here is OH. If we have that group is OH, we have said the alcohol of methadone drastically reduces the activity. So the alcohol of methadone drastically reduces activity. But now when you acetylate the alcohol of methadone, that's the one we have just mentioned before, just before here, that reduction of the ketone produces methadone with decreased potency. If you reduce, you have to cleave the ketone and you will get an alcohol, and that has reduced activity. But now if you acetylate that alcohol to get the methadone, then the resultant compound has good activity. I just wanted you to understand how you are getting the level methadyl acetate. I'd already mentioned it before, but the way you are getting it is if you are to cleave there, you will get the alcohol. You will get the alcohol of methadone. When you get the alcohol of methadone, then you acetylate. Acetylating means you add an acetyl group. You add an acetyl group. Remember, in methadone, this group here, that group there is a ketone. Remember, in methadone, that group there is a ketone. And all we are doing is the alcohol. First of all, you reduce it to an alcohol, then you acetylate it. So you can still see that group there is retained. So once you acetylate that group, you get the compound we call methadone acetate. You get the compound we call methyl acetate. And all we are saying is that acetylating the alcohol produces a more potent analgesic compared to the alcohol derivative. The laboratory isomer, again the same, is marketed as levomethadone. Remember, with these compounds, the levo isomer has much more activity than the dextro isomer. The levo isomer is marketed as levomethadone acetate. A single dose can suppress withdrawal for 3 days. Remember, we have said that these drugs, the phenylpiperidines, do not precipitate withdrawal symptoms. They do not precipitate withdrawal symptoms. So if you give them to people who have been abusing opioids, they are able to suppress the withdrawal symptoms, yet these people will have the same feelings, but they will not have withdrawal symptoms. So they are able to suppress withdrawal symptoms for 3 days and is used in the rehabilitation program. So again, I believe when you go to Mathare, most probably you will come across this drug, which we are calling levomethadone. The levo isomer is 5 times more potent than the dextro isomer. Again, if you look at this drug, how are we getting the levo and dextro isomers? Of course, this is a chiral center there. It's a chiral center there. Also, this is a chiral center there. So this drug can exist as either the levo or the dextro isomer, and we are saying the levo isomer has much, much more activity than the dextro isomer. So again, that is another drug whereby it is still a derivative, and we did draw it a derivative of methadone. If you look at it, it's a derivative of methadone because that structure is the same. The only bit of structure we have changed is this area whereby, first of all, this was a ketone, C double bond O, C2H5. And then instead of that, what we have done to that ketone, we have reduced that ketone and made it into an alcohol. Let's go to methadone. So here we have the structure of methadone. There is a structure of methadone. You can see this is a C double bond O there, and then C2H5. So what we have done to that drug is that group here, first of all, we reduce it to an alcohol. So it becomes an OH. And then after it becomes to an OH, it is an alcohol. Then you acetylate it using acetic acid. Once you acetylate it, then that is how you will add your O, C double bond O, and CH3, CH2. So you use propionic acid, sorry. So you acetylate it using propionic acid. And once you do that, then the alcohol will be changed into the ester. And that is what you have for the levomethadone. So please do understand how the slight difference, because if you look at, of course, the methadone, if you look at the methadone, the C2H5 is part of the ketone, But of course, now when you come here, you find that there is that substituent, because that substituent, and then you have changed that into an alcohol and then acetylated that alcohol. So that means that's the main difference between the two drugs. So that levomethadone, again, an important drug, just like methadone, used in rehab centers. Then we move to I think this might be one of the last drugs within this category, but a bit different, propoxyphene. If you look at your, pain medications, when you go out there, you will see the drug we call propoxyphene, and mainly dextropropoxyphene. Remember, when we want to avoid the analgesic properties, the opioid properties of these narcotic analgesics, we take the dextro rather than the levo. Take the dextro rather than the levo, knowing that the dextro isomer is just the stereochemistry Instead of the levo, you take the dextro. We have realized that the dextro isomer are better antitussives than the levo isomer. The levo isomers have very high opioid interaction and, of course, liable to abuse, and also, of course, giving us a lot of toxicity. So when we look at this drug we call propoxyphene, we will see quite a number of changes. One of the changes we see is that this is a benzyl group. Remember, we have already mentioned that when you change, you have not completely removed the ring, but you have replaced the phenyl ring, which is in methadone, with a benzyl ring. And that, of course, that benzyl ring, remember we said, of course, we still have one of the phenyl rings, but remember we said the other phenyl ring is also responsible of giving us a maximum optimal orientation between the terminal nitrogen and the phenyl ring for giving us the best activity. So when you change that phenyl ring and you put a benzyl ring, you interfere with the distance, with the optimal binding of propoxyphene with the opioid receptor. So that is one change. Then, of course, when you look at it again, compared to methadone, methadone has its methyl group at the alpha position. It has its methyl group at the beta position. That further reduces the analgesic activity of that compound. And then the other change is that if you look at this compound, it is the ketone which you had at this position is replaced with an ester. And not only is it replaced with an ester, of course, the ester is a reverse ester to give it a little bit of a stability. Remember, we did mention that reverse esters are more stable than the normal esters, where you start with the C double bond O and then the oxygen. So you put a reverse ester to give it a little bit of stability, but again, once you change the ketone to the reverse ester, then you further decrease the activity of these compounds. And hence, therefore, propoxyphene has minimal analgesic or narcotic analgesic activity or opioid characteristics, and therefore, as dextropropoxyphene, it is an additive in cough mixtures for antitussive activity. So potency decreases dramatically or drastically. There is potency increasing drastically. We have said the phenyl replaced by a benzyl. The methyl has been moved to a beta position. The ketone is replaced with a reversed ester, and therefore that drastically decreases activity. Because if you look at the SAR, we have mentioned all those groups, and we have said they are necessary for maximum activity. Introduction of benzyl creates a second chiral center, of course. If you look at when this was a phenyl ring, this was not a chiral center. So if you look at this, oh, sorry, I had even said it was a chiral center. Why didn't you correct me? Sometimes you should correct me, because when you talk much, you can make a mistake. Of course, it's not a chiral center, because this is a phenyl group and that's a phenyl group. So this compound has only, how many chiral centers does it have? Of course, it has this chiral center there. And of course, you have created a new chiral center there. So those are the two chiral centers. But this is not a chiral center because of the fact that this has two phenyl groups. But of course, now this has an oxidant. This is a chiral center. And of course, this is a chiral center. But for propoxyphene, you can see the group you have introduced there. So that group is different from the phenyl group. So, of course, we have a chiral center there. The chiral center that was found in this other drug has been destroyed. You can see there's no chirality there. Because you have put a reverse ester, we are starting. So we had the group which had been introduced, like in methadone, came in with a chiral center, but here we do not have any chiral center. That group does not introduce any chiral center, but we still also have the other chiral center at that position there. So the propoxyphene also has two chiral centers, and it will require a certain absolute configuration for us to get maximum, or to get the levo isomer, which will have a little bit more activity than the dextro isomer. So we are therefore saying the benzyl creates a second chiral center with four possible isomers. The analgesic activity resides preliminary in the analgesic activity resides preliminary in the dextroisomer with the 2s 3R configuration. It is marketed as that. It has 1/8 the potency of methadone and 2/3 of codeine, has low addiction ability and toxicity. So this one is the liver isomer with 2R 3S configuration was used as an antitacid. So this one even changes, even the not only even the stereochemistry is actually changing completely, because you can see it is a dextroisomer. To see that, to note that difference. It is a dextroisomer. The analgesic activity is primarily it's a dextroisomer actually with the configuration. I'll show that in a minute. 2s 3R configuration, which has analgesic activity. So therefore, this compound is completely different. Even its stereochemistry, absolute stereochemistry is different, because in all the other compounds we have seen that it is a lipoisomer that has maximum activity. There is one set of compound where we did say that the dextroisomer has activity, but in majority of them, it is a lipoisomer. So for propoxyphene, because of change of that, the structure, we find that the dextroisomer is the one which has analgesic activity, but very low also, even compared to morphine. Very low. It has 1/8 the potency of methadone. Methadone has, we say it has almost equal activity to morphine. 1 out of it, that means it has very low analgesic activity. We can be able to account for its low analgesic activity compared to methadone. We have already explained, and therefore it will also have very low addiction liabilities and toxicity, because the toxicity is proportional to the analgesic activity. Then we are seeing the lipoisomer. So you can see it's just a difference. 2R 3S configuration was used as an antacid called that's just a brand name, which lacks the classical opioid characteristics and is purely an antitussive. So please let us be reminded, let us remember the reversal of the stereochemistry, whereby it is the lipoisomer which has antitussive activity, and it is a dextroisomer which has an analgesic activity. The napsylate salt is used because it is water insoluble and is less likely to be abused through injection. So just as we talked about loperamide, you can use a particular salt you can use a particular salt so that you prevent abuse. But for loperamide, we did not say the salt. We say the way it is, with its low water solubility, it cannot be abused. But we are saying here you can also derivatize a drug into an insoluble salt. And once you derivatize it into the insoluble salt, then it cannot be abused. So this is a drug we are talking about, to look now at its proper stereochemistry. So we have here is our position 2. Which are we considering as our position 1? Position. I think perhaps we are starting from here 1, 2. Yeah, it could be we are starting from here and giving that, because I cannot see any other position we can call position 1. So I think we are starting from this carbon there and giving that position 1, because there is no other carbon anyway. Position 1, that we are giving it position 2, position 3. Because we had said position, let's see. In the methadones, we were calling this position 6. And this one we are calling position 5. So there is a slight difference in the numbering. We'll go back there. But we are just saying we are numbering this. I believe we are numbering that as position 1. And because we are looking at the alkyl group, and the alkyl group moves like this. So they have numbered, instead of numbering from the one, because instead of numbering it from the nitrogen, they're actually numbering from there. And of course, at position 1 is where we have one of the phenyl substituent. At position 2, we have the other phenyl substituent. So we are just still looking at the longest alkyl chain, and we are moving like this. And therefore, calling that carbon position 1, calling this carbon position 2, and calling that carbon position 3, and so on. And we are saying optical activity. So when we look back, for us to get the correct activity. Let us look at the correct activity here. So we are saying the dextroisomer, we had mentioned somewhere, and in the dextroisomer is 2s. So note that somewhere. And the dextroisomer, dextro is 2s and 3r, which means the levoisomer is 2r and 3s. That's the only difference. So the dextroisomer is 2s, 3r, and therefore the levoisomer will be the opposite, and the levoisomer, which is the one we are saying has antacid activity, is 2r, 3s. So just important for us just to remember. So we are saying our dextroisomer is the one which has 2s. So you can look at this. This is the s, and this is the 3. And therefore, that's why we are calling it dextro. So the dextroisomer, 2s and 3r. And the dextroisomer is the one which you have said for this one has antitussive, has analgesic activity as opposed to the other compounds that we have looked at. And of course, the levoisomer now, the position 2 will be R and the position 3 will be S. So this was just to show the stereochemistry of propoxyphene. And of course, to account for those chiral centers is because we are saying this group there is different. It is a benzyl group, allowing that position there to have chirality. Of course, we do have a methyl group there at that position, an alpha methyl group, again allowing that position to have chirality. And of course, the 2s, 3r being our dextroisomer, and that dextroisomer is the one which does have analgesic activity. Then we have mentioned of the propoxyphene naphthalate. Some naphthalate, I just looked for the structure so that we can be able to see, and you can see indeed the naphthalate increases the lipid solubility, and therefore that formulation, when propoxyphene is formulated as the propoxyphene naphthalate in the market, or you have it propoxyphene naphthalate, then it has very poor water solubility, and therefore the drug addicts, they normally just add water, make it into injectable, push it into their veins. So it cannot have any abuse potential because of the fact that it is insoluble in water. Therefore, if it is insoluble in water, it implies that you cannot form it into a solution, and therefore you cannot use it parenterally. So that finishes again the phenylpropylamines, and of course of importance is to understand the various structural modifications. Please draw all those structures. We have gone through them, and these compounds again have a variety of compounds. You can do various structural modifications. In some of the times you maintain the activity, but you can even do a structural modification up to the point where you get levopropoxyphene, dextropropoxyphene, again where you can use the dextropropoxyphene. You can use the levopropoxyphene, you can use the levopropoxyphene for antitussive activity. Structural modification, telling us it's very important. The structure of the molecule, very, very important, because indeed it can determine the kind of activity that you can get from that compound. So please note those structural modifications that can be done. So we started from morphine, and from morphine, we looked at the peripheral groups. We looked at the nuclear groups. So we looked at the peripheral groups of morphine initially to get the morphine analogs. We looked at the peripheral groups, the hydroxyl group at position 3, the hydroxyl group at position 6, the double bond at position 7, 8, the terminal nitrogen. We looked at all those groups, and we were able to structure and modify those groups as with morphine the way it is. And we were able to get quite a number of compounds which had differences in their activity. Remember the oxymorphones, the oxycodones, and so on, able to hydrocodones. And so we were able to get different compounds which were able to give us different activities. And then from morphine and its analogs, again, now we came to the nuclear. And the first thing we did is removed the epoxy ring. We're able to remove the 4,5 epoxy ring. And in removing that ring, what did we say? it does not have major activity difference in terms of binding the receptor. Indeed, it increases, it improves on the activity of the resultant compounds. So we were able to get the morphinans. But even as we mentioned the morphinans, of course, we did say the morphinans also had several structural changes. In that, of course, the 7-8 double bond was not there. The hydroxyl group at position number 6 was not there. Again, knowing that the changes of those groups again further increased activity. Then we came from there, from the morphinans, we went on and we came to the benzomorphins. And in the benzomorphins, what did we do? We removed the whole of ring C. And we did mention, so we've removed ring C, we have removed also ring E. And we are saying again, these molecules obey to some certain extent the morphine rule, especially, of course, with the fact that you must have some substituent at position number 5 and position number 9. So we removed again that, and we had again several examples. And within that class, which we call the 4-phenol piperidines, we have also come the subclass of the anilidopiperidines. Then from there, we have now come and we are kind of mutilating the whole of them, the whole morphine molecule, because we are only left with the one phenyl ring, with an addition, of course, of a second phenyl ring, and with a straight chain, with the terminal nitrogen being part of the straight chain. Again, we are saying, even within that class of compounds, which we are calling the phenylpropylamides, we are saying we can still do a lot of structural modification. We are saying that the dimethyl amino group being the best, but the nitrogen can also be part of a heterocyclic ring, the piperidine ring, the also morphine ring with retention of activity. Then from there we have seen we can also still change the 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 uh, the, the straight chain which contains the nitrogen, whereby we can shift the methyl group. We can shift the methyl group to different positions with change in activity. We can also, now as we have seen, the last compound, change one of the phenyl rings. Change one of the phenyl rings, change the substituent from an ester to a ketone, and still have some degree, not very high, but small degree of analgesic activity. And if we change the stereochemistry appropriately, we can be able to develop a compound which has more antitussive activity with change of stereochemistry from levo to dextro with a max with for that compound with, of course, retaining of minimal analgesic activity. And when we change the stereochemistry and we change the stereochemistry and we get the levoisomer, then the levoisomer will be able to give us antitussive activity. What am I saying? I'm saying morphine, being the naturally occurring compound, is very bulky, very bulky. And there are portions of that molecule that we can do away with. And finally, we are left with only those areas which are the pharmacophore. The pharmacophore, or those areas of morphine that must be there to interact with the receptor for us to have activity. And some of those areas we have seen is that you have a phenyl ring, you have a quaternary carbon, you have two carbons separating the terminal nitrogen and the quaternary carbon, which also sometimes there are exceptions, and you have a terminal nitrogen. So at the finality of it all, we are saying we can have such a molecule, which when compared to morphine is very simple, but it can still give you activity. Of course, as we have said, depending on the substituent, the activity of that molecule can be equal to the activity of morphine, or even much more than the activity of morphine, depending on the substituents that you have on that molecule. So that indeed closes. What has happened? Yeah. Goodness, yes, man. Oh, oh. Wow. I don't know what has happened to my molecule. Wow. compound, and now you can be able to analyze because you know the morphine rules. We can see, does it completely obey the morphine rules, or does it obey the SAR of the phenylpropylamines? Because indeed it is. It is a phenylpropylamine. Does it obey the rules? And indeed it doesn't, because we know for the phenylpropylamines to have maximum activity, we need another phenyl group there, which is not there. And that means when that happens, then you have that position being a quaternary carbon. So when we look at that compound, in fact, that I think is the only option that it has. And of course, to compensate for the slight loss in activity, it adds another hydroxyl group. Remember, we did mention hydroxyl group is not necessary for binding of the benzene ring at site D. But of course, anytime you have it, like in morphine, it can interact with other polar areas through hydrogen bonds. So that can compensate and increase the activity again a little. But if you look at that compound tapentadol, we can be able to say that the lower potency of this compound compared to morphine, and because remember, methadone and morphine are almost equipotent. So the reason why this compound will have lower activity than morphine is the fact that it has lost the second. It has lost a second phenyl group, because with that second phenyl group, you will get the structure of methadone and methadone. Of course, also the other one is, of course, the shift of this group, because in methadone, that group is there. So those two things have made that compound lose a bit of its activity, has lower activity than morphine or methadone, but of course, with the compensation of activity because of the introduction of a hydroxyl group on the phenyl group. But nevertheless, does not compensate enough. That molecule will have much lower activity than morphine. When it does so, then it will have better tolerability and lesser side effects. So all we are saying, but if you look at quite a number of the other properties of the other characteristics of the drugs which obey the morphine rule, you see that they are there. That is a nitrogen, and this is supposed to be the quaternary carbon. Of course, it is not, but you can see the terminal nitrogen and that carbon separated by two carbon atoms. You have the terminal protonable nitrogen. So it does obey. It has one phenyl ring. It does obey partially the rules, but it doesn't obey all of them, and therefore that results. I hope that result in that compound having much lower activity. So given a structure, even if you have never seen it, you can't be able to account for its analgesic activity or its antitussive activity if it has an antitussive activity, because we did mention that most of the compounds antitussive activity are the ones with a methoxy group at position number 3. And I think with that, we can comfortably say I went through, when you couldn't hear me, I think I discussed all the compounds, but never mind, you have all of them. So this is the receptor that we have been discussing. And you can see these is our phenyl group there. And you can see the phenyl group interact with the receptor D. And then we have these other hydrophobic areas. They can interact with the receptor C. We have the terminal nitrogen protonated interacting with our receptor B through anionic bonds. And then, of course, when we have the phenyl ethyl, or when we have the group that we had in buprenorphine, then you find again that phenyl group is able to interact with the receptor A. Kindly confirm. I don't know whether we discussed, because I don't want to go back, but confirm how the phenylpiperidines interact with the receptor as compared to the phenylpropylamine. Just compare, and I will summarize it next time in case there is any difference. I think we discussed it properly. So with that, because I wanted us to really finish this unit, because we have also mentioned these compounds. Of course, we have the narcotic antagonists, and of course, we have mentioned them as we were discussing the other compounds, because the narcotic antagonists are developed through the change of the group that is on the 17 on the nitrogen, on the terminal nitrogen. So if you remember, the compound we were starting with was the oxymorphone. Of course, we also can start with the morphine and we can get naloxone, but we started with the oxymorphone. And when you look at the oxymorphone, it has a hydroxyl group at that position. It has a ketone and remove the saturation of the double bond. And the oxidation and saturation of the double bond, especially the saturation of the double bond, changes. Remember, we said in morphine, ring C has a boat conformation. When we remove the double bond, then ring C attains the chair conformation. And the chair conformation, as we're going to see, is able to interact with the receptor a little bit better. When you look at the oxymorphone, that is a methyl group. When you change this methyl group and you increase it to either from, we did mention, from 3 to 5 carbon atoms, then you attain an antagonist activity. And if you look at now bufine is just that compound whereby you have the hydroxyl group at that position, increasing the binding. You have that group there, but the hydroxyl group is maintained at that position. Then if you look at the terminal nitrogen, it has a cyclomethyl butyl substituent. And remember, when you have that slightly bigger group, it brings in antagonist activity rather than agonist activity. So we have nalbuphine, we have naloxone. If you look at naloxone, but of course, nalbuphine is not a pure antagonist. It still has some agonist activity. But when you look at naloxone, again, naloxone is the same, whereby we are starting from oxymorphone, and from the oxymorphone, again, we put the allyl group at that position. Remember, we didn't mention when we put an allyl group at position terminal nitrogen or at position number 17, we change the compound from agonist to antagonist activity. And indeed, naloxone is one of the pure antagonists. Then you have naltrexone, again, also a derivative of oxymorphone, but we have the cyclopropyl methyl group, and the cyclopropyl methyl group gives this compound even much higher antagonist activity as compared to naloxone. Then you also have nalmefene, and when you look at nalmefene, we acknowledge this change here, that change there. So that change there, where now we have completely removed the oxygen, which we really do not need, and we put an alkyl group, this nalmefene will have slightly higher lipid solubility. Higher lipid solubility. It will also have much better interaction with the receptor, and therefore with the hydrophobic receptor, and therefore giving us much better an antagonist activity. Remember, because of this group, it still has antagonist activity. But all we are saying is that those groups you are putting are enabling this molecule still to bind. They bind, even antagonists must bind with the receptor, but will not trigger agonist activity and therefore behave as an antagonist. So therefore, the change in the groups is allowing these antagonists to bind the receptors, be it the mu receptor, much more strongly, but of course they do not elicit or do not bring about an agonist reaction. They block the receptor, bind the receptor well, and block the receptor, and they are able to block the receptor because of this group. So this group is the one which is responsible for blocking the receptor. As you can see, these are the groups. Then oxymorphone is an agonist, but the minute you change the group at the terminal nitrogen, you change from agonist to antagonist, either partial agonist to mixed antagonist, agonist, and then finally you change to the antagonist molecule, where we have naloxone, naltrexone, and nalmefene. So the points I've just discussed. So this also will refer to the other drugs that we mentioned, as long as they have these groups. So all we are saying, if you look at this compound, whereby you have a double bond at that position and you have a ketone, you can see this group there has a boat conformation. And the boat conformation, this site here is supposed to be a hydrophobic site. So the boat conformation tilts this oxygen and it goes to the hydrophobic site, and of course it doesn't bind very well. So when we remove the double bond, and we remove the double bond from ring C, then you find now ring C acquires the chair conformation, and this chair conformation is able to remove the hydroxyl group from the hydrophobic binding, and it gets near its own polar site, and therefore it can't be able to interact with that polar site. And that is why we said when you have a drug where you saturate that double bond, like in the dihydromorphines, where you saturate that double bond, then you saturate that double bond, then you find there is a slight increase in activity, because all that happens is the boat conformer changes to the chair conformer, and there is better interaction of the hydroxyl group with its own polar site, rather than going to the hydrophobic site, and it cannot be able to interact with the hydrophobic site. Now, further, so this is just when you saturate, and you still are left with the hydroxyl group. When you saturate now and you oxidize, now this is a kind of thing you get. So not only do you get the chair conformer, but also there is a slight change in the shape, and the ring, the ketone group, is able to properly be within the polar site and leave completely the non-polar site to interact, for the non-polar site to interact with the hydrophobic areas. So it leaves the non-polar site to interact with the hydrophobic areas. You can see here the hydroxyl group is interfering a little bit, and is not completely able to interact with its own polar site, but here it moves. It's able to interact completely with its polar site. Then now, when you make it now methane, again you still maintain the chair conformation, and again, as we have said, the methylene group increases the lipid solubility and increases the interaction with the nonpolar or hydrophobic site, and I think that is site B, giving us very good activity. So those are the changes when we change the peripheral changes, and these peripheral changes, you find that they are also there in the antagonists. That's why I've mentioned them now, because all the antagonists of that group saturated, and they also have a ketone at that position. If you look at all of them, they are derivatives of oxymorphone, whereby that is oxidized and that also is reduced, or saturation, or there is saturation, which is equivalent to reduction for maximum activity. So the question is, and we needed to understand, what does that do? What does the saturation there do? What does the oxidation there do? What does the additional methylene group in place of a ketone do at that particular position? Because those are the things that have been done. Of course, the other thing in all of them is that they have that hydroxyl group there, and that hydroxyl group also increases in binding. So now we are able to mention that we are replacing the hydroxyl group with a methyl or methylene, and this is hydroxyl group. This is like inalmethane. Increases the mu receptor affinity, again, due to better hydrophobic interaction, as I've already said. Also, it will increase the lipid solubility slightly. For example, nalmethane, introduction of an additional hydroxyl group at carbon 14, as we have already discussed. In all of them, they have a hydroxyl group at position number 14, increases the mu receptor affinity due to an increased hydrogen bonding to an allosteric site. The carbon 7, carbon 8 double bond or aphinic bond saturation changes the lipid water partition coefficient and mu receptor affinity. Remember, saturation, you add hydrogen, so slightly increase the lipid water partition coefficient, and also you change the mu receptor affinity, because, as we have said, you change from, when you saturate, you change from the boat to the chair conformation. Saturation gives a slight increase in the lipid water partition coefficient, And also ring C goes from both to chair conformation that changes the 3D position of carbon C hydroxyl group, increasing, as we have seen there, we've explained there, changes the position of the 6 hydroxyl group, increasing the interaction, increasing its interaction. So goes from both to chair conformation that changes the 3D position of carbon 6 hydroxyl group, as we have said, and therefore it has been completely removed from interacting or influencing the hydrophobic area, which is supposed to be interacting with the hydrophobic groups. This gets rid of the unfavorable hydrophilic hydrophobic. You see, hydrophobic is where the hydroxyl group is interacting with the hydrophobic area because it does not interact well. Thus, this also increases mu receptor affinity. Saturation plus oxidation, where now we have saturation here plus oxidation, as found in all the narcotic antagonists of carbon 6 oxygen, produces an increase in mu receptor affinity. The ketone is more rigid and held away from the hydrophobic region, may even interact with an adjacent hydrophobic region. So once you saturate, again, you can see it is pushed to its own area, and it is pushed such that it has no influence with the hydrophobic area and allows the groups which are hydrophobic to interact with the hydrophobic receptor. So those are, and that happens not only for the narcotic antagonists, it will also happen for all the narcotic agonists that have those groups that we have discussed at those positions. So replacement, therefore, of the potent narcotic agonist, oxymorphone, because that's where we are starting. Remember, the starting group compound is oxymorphone. I've just explained why we are starting with oxymorphone. It has better interaction with the receptor. I've explained how it has that. So if you replace the N-methyl group with an allyl group, once you do that, you get your naloxone. If you replace with a methyl cyclopropyl group, you get your naltrexone. If you replace with a methyl cyclobutyl group, you get your nalbuphine. Then there is introduction of antagonist activity. So results in emergence of opiate receptor antagonist activity. So that group at the final position, number 17, is the one responsible for antagonist activity. The pure opiate antagonists at mu, kappa, and delta receptors include naloxone, naltrexone, and nalbuphine. The others can have some agonist activity at some of the receptors, and therefore they are not pure opiate antagonists. Pure antagonists are used for the reversal of the narcotic and respiratory depression induced by opiate agonists, as well as psychotomimetic action. So when you give the antagonists, it is like when somebody has abused, is an abuser of these drugs, of the opioids, you give them this antagonists, and they will be able to reverse the respiratory depression and even the narcotic, all those side effects that are due. We did mention all those side effects that are due to the narcotic analgesics. These compounds are also used as adjuncts to the maintenance of an opiate-free state in detoxified, formerly opiate-dependent patients. So you can use them as antagonists to reverse the effect, or you can use them as maintenance of opiate-free. So somebody who wants to maintain the opiate-free condition, you can give them these drugs so that they are able to get free of the narcotic analgesics. You will do a lot of this in pharmacology. Then we look at naloxone. We just mentioned one or two things about it. It is administered IV or IM, so it's not orally active. It has very low oral bioavailability. And if you look at the group it has up there, it has a double bond. And you know, double bonds undergo very readily undergo metabolism. When you have a double bond in the allyl group, it is a site highly susceptible to metabolism. So it has slow action and relatively short duration of action. So that is naloxone. Then if you look at naltrexone now has a cyclopropyl methyl group. It is used orally. It has a substantially longer half-life compared to naloxone. It has a longer duration of action, And so it is, so that is now naltrexone. So naltrexone has a slight advantage of naloxone in terms of it is orally administered, it has a longer duration of activity. Then we have naumifene. I think I have it on its own. Naumifene, which is also a pure antagonist. It has also higher activity than naltrexone. We can understand why, because you have replaced the oxygen with a methylene group. You have improved on the interaction of naumifene with the hydrophobic site at that position. And of course, also you have increased the lipid solubility by replacing the oxygen with a methylene group, as we have already discussed. So it has a higher potency for opioid receptors than naloxone and even naltrexone. It's about 4 times higher potency than naloxone for the mu opioid receptors, and slightly more potent at the kappa opioid receptors. The naumifene has also a longer elimination half-life than naltrexone, and we have explained why. We cannot say we do not understand. It has some advantages over naltrexone, higher bioavailability because of the higher lipid solubility, more effective binding to central opioid receptors. It is also not hepatotoxic in a dose-dependent manner. So it has those advantages as compared to naltrexone. But that doesn't mean naltrexone. I think naltrexone is quite commonly used. And these drugs, when we look at them, almost all of them will undergo similar metabolism. They can undergo 3-O glucuronidation. Remember, all of them have a 3-hydroxyl group. They are morphine derivatives. They are morphine analogs. So they will require the hydroxyl group at position number 3 for activity, and to a lesser extent, they can undergo also oxidative end dealkylation. And indeed, I think that's my last slide. Wow. Yes, that's my last slide. I was praying that it's not that we don't have power. So that's our last slide. I hope you can appreciate the antagonist, you can appreciate the agonists, you can be able to account for the activity, for the antagonist activity of those drugs. You can also be able to account for the reason why we are saying naumifene is one with the highest potency compared to the other ones. And of course, at the same time, they do require, all of them have the oxymorphone structure, so that we are already starting with these drugs having very good binding, having very good affinity for the receptors compared to morphine. There was one little thing I remember I left behind. That's why I'm going back, so that now we finally look at their classification, because there was one slide which was missing when we were looking at their classification, because I really want us to finish today, because we need to move to another class. The class, yes, here we are. We need to move to another class, and I believe we will move to the anti-Parkinson's drug, and therefore I need you to classify for next lesson. I've given you the assignment, just 2 simple questions you should answer very quickly, so that I can mark that assignment. And then, of course, as a class exercise for next time, because when we draw these structures earlier, it becomes a little bit easier for us. So I will require you to classify the anti-Parkinson's drugs. Of course, you classify them, and once you classify them, and also draw the structures. So you classify them and also draw their structures, and that way we will be able to move faster. So when we were looking at the classification of the narcotic analgesics, again, the classification is not cast in stone. Sometimes you will find you might talk about a partial agonist, and it can also be considered as a mixed antagonist drug. So it's really not cast in stone, and sometimes there can be interchange. But of course, for some of them, they are what they are. So based on receptor interaction and source, and we can talk about the naturally occurring antagonists, and the naturally occurring, of course, we call them the opium alkaloids. We have morphine and codeine. These ones are naturally occurring. Then we have the semi-synthetic And of course, we're first of all looking at the pure agonist, because we are looking at the receptor interaction in terms of, is it an agonist, is it an antagonist, is it a mixed antagonist, or is it a partial agonist? And that's where I said, when it comes to mixed agonist, antagonist, and the partial agonist, sometimes they are really not cast in stone. So when we look at the pure agonists, and which are naturally occurring, we talk about morphine and we talk about codeine. And then we can look at the semi-synthetic, whereby we have structurally modified morphine, then we have the hydromorphone, we have the oxymorphone, oxycodone, and many others which we have looked at. These are just examples of semi-synthetic analogs of those drugs that are pure agonists. Then we can also look at the synthetic compounds, because we have gone down up to the bottom, and now we have some synthetic compounds which are also agonists. We have meperidine, levofenol, methadone, sulfentanyl, alfentanyl, fentanyl, methylphentyl, and levomethadine. Of course, there could be others, and indeed now it makes more sense, because we have looked at all, we have mentioned all these compounds. There is none of these compounds that I have not mentioned. So when we say they are synthetic, it means they are not semi-synthetic, they are purely synthesized in the lab. And those are the synthetic compounds that are also pure agonists. Then from there, we can move to the mixed agonist-antagonist drugs, mixed agonist-antagonist drugs, and under the semi-synthetic, we have now B5. Now, of course, we have no naturally occurring, because the only naturally occurring is morphine and codeine, and of course, the agonists. So we start with the semi-synthetic, where we have nalbuphine. I hope from this structure you can be able to draw this structure. Remember, nalbuphine has a methyl butyl group at position number 17. At position number 14, it has a hydroxyl group. It has saturation. At position 7-8, and it does not have any hydroxyl group or ketone at position number. No, it has a hydroxyl group, at position number 6, and that is why we call it a fine, because it has some similarity with morphine. So it has a hydroxyl group at position number 6, but it has also a hydroxyl group at position number 14. Then you have naloxone, again a derivative of morphine, but the difference here is that naloxone has an allyl group. The group where we have CH double bond, CH, and then CH bonded, CH2 bonded to a CH double bond. CH2, it has that. Otherwise, it has the same structure as morphine. The only difference is that it has that group at that position. And because of that, we are saying these are mixed agonist, antagonists. When they bind the receptors, they can be responsible. They can bring about agonist and antagonist activity. And then synthetic, we have pentazocine and butorphanol. Again, thanks. We have mentioned all these drugs. If you remember, I hope you can remember which class is pentazocine and which class is butorphanol. Can you tell me in a minute? In which class is pentazocine and in which class is butorphanol? I've not even asked you even the slightest question. Oh, now this one I will answer with two, but first answer my question. In which class is butorphanol? And all is hydrophilic, and because it's hydrophilic and it's almost falling within the lipophilic area, you have the hydrophilic lipophilic interactions, which are not very good, and therefore nalbuphine will have slightly higher activity because of the fact that, one, the group that you have put, which is a methylene group, is lipophilic. It is increasing in the lipid water partition coefficient, and therefore in the permeability or in the penetration of that molecule through the lipid barriers. Number two, we are saying in adding that methylene group, you are also improving on the interaction of that molecule with the lipophilic or hydrophobic site within the opioid receptor, and therefore no wonder nalbuphine has slightly higher activity compared to naltrexone, which also we said has slightly higher activity than naloxone. The naltrexone and naloxone, the comparison or the difference is coming in because of the substituent at position number 17, one of them being a little bit bigger than the other. So I hope that has answered your question, Tua. So pentazocine, yes, thank you. Pentazocine, of course, is a benzomorphan whereby we have we have removed the ring C, and butorphanol is a morphine. And thank you, at least you are remembering. So all we are therefore saying is that it is important to remember when you see that the name gives you a specific structure. So we are therefore saying the mixed agonist antagonist we can consider pentazocine and butorphanol. There are sometimes which say butorphanol is a partial agonist, but for now we will classify it as a mixed agonist, antagonist, and all we are saying it has have agonist activity at some receptor and antagonist activity at other receptor. You can find that they might have agonist activity at the mu receptor and antagonist activity at the kappa receptor, or even the opposite sometimes happen. So, when we talk about mixed agonists, antagonists, is because they interact with the kappa receptors and the mu receptors with some slight difference. Then we have the partial agonists. We have only the semi-synthetic, and remember, we did mention buprenorphine. Buprenorphine was in which class? Can you remember? Buprenorphine was in which class or in which category? Do you remember? Buprenorphine? Talk to me. Buprenorphine? Thebanes, very good. At least you're somewhere. Or ripavines or the thebanes, whereby we said there is an additional substituent at position number 7, and there is also annulation. And I hope you can remember that. And we said because of that, those compounds are have very high narcotic properties, narcotic analgesic properties. So we have the buprenorphine, which we can categorize as a partial agonist. As I have said, not really cast in stone. Sometimes you find that butorphanol in some of the books could be classified as a partial agonist. Semi-synthetic, again, narcotic analgesics, we have agonists, antagonists, we have just looked at them, naloxone, naltrexone, and nalmefene, and they do not have agonist activity at any of the opioid receptor sites. They block the opioid receptor, inhibit pharmacological activity of the agonist, and precipitate withdrawal in dependent patients. So they precipitate withdrawal in dependent patients, and therefore they are completely antagonists. They do not have any agonist activity. And when we look at some of the compounds, definitely we can look at this, and this is our nalbuphine. As we have said, you can see it has the hydroxyl group at that position. And because of that hydroxyl group, of course, it will have slightly different activity as compared to naloxone, because the hydroxyl group although this will have it will definitely have the chair conformer, but the hydroxyl group will terribly interfere with the binding at the hydrophobic area. But when you look at it, it also has what is found in the other antagonists. It has the hydroxyl group and has that group there at that position. And then we have, this is the naloxone, and this is nalbuphine, this is naloxone. And when you look at naloxone again, completely resembles, so it has that group and completely resembles morphine, has a double bond at position 7-8, has a hydroxyl group at position 6, and therefore will have much lower activity as compared to the nalbuphine. So naloxone is a mixed opioid agonist, antagonist. It acts at 2 opioid receptors, the mu receptor. It has antagonistic activity. As I told you, they can have either agonist or antagonist activity. It has antagonist activity at the mu receptor, and at the kappa receptor, it has high agonist activity. So you can see mu antagonist, kappa agonist. Pentazocine also has weak antagonist or partial agonist activity at the mu. So you can antagonist or partial agonist activity at the mu opioid receptors with the full, again, agonist activity at the kappa, at the opioid receptor. So very very, very similar, but you can see they have agonist and antagonist receptor activity. So they have both agonist. We are calling them mixed agonist antagonist because they have that agonist and antagonist receptors at the different receptors. So we have nalorphine, we have pentazosine, we have nalbuphine. I also think I had some 1 point or so somewhere I mentioned about butorphanol. Let me check where that point is for butorphanol. Just want to make sure I give you all the points. There's somewhere I mentioned butorphanol. Somewhere. Yes. So we also have butorphanol, which we had said has stronger agonist than morphine, and also it's a weak antagonist. So it's a partial agonist and partial antagonist activity at the mu-type opioid receptors, as well as antagonist and partial agonist at the K opioid receptor. So you can still see it has both agonist and antagonist activity, and that's why we are calling it a mixed agonist antagonist, because it has both of those activities. So even butorphanol was also fitting in that category. So I think that is the only thing I had not done. Then, of course, the antagonists, we have just discussed them. So that now, with us having looked at all the compounds, I think it's also much easier for us to understand. Then when you look at even cyclophan, narcotic antagonist, but it can also, it has mixed strong agonist than morphine. So it also quite a number. You can have quite a number of them which have mixed agonists, antagonists. But remember, we did mention because of the hallucinogenic activity, that compound also has no use. So you can have many other examples, but I've only quoted the ones which have appreciable in that category. They really fit well in that particular category because they have appreciable of whatever activity that we have discussed. Are there any questions? And that's you already told me where buprenorphine exists, where it falls. Then I have answered. There was one question which had been asked. I hope I have answered it well. I think it was Mutua. I hope, Mutua, you are satisfied. Is there any other question? Because with that, we will close. There's one drug I have not discussed, tramadol. It is also in this class, and I have asked you, the assignment is on tramadol. So kindly discuss tramadol. And then, of course, the other small assignment I've given you, if you are done with it within 1 week, the better. If you have to, because for purposes of marking and purposes of marking. So now I think if you are okay, if you are happy with the narcotic analgesics, we can then therefore sign in. If you are not happy, please let me know. You are my old students. You're not like the ones I'm teaching new. You are my old students. I've been with you for a long time. So if you are okay, kindly uh, say so. If you have any issues also, it's good always to be free and talk your mind. So do not